back to part 2 of the properties of metal complexes or properties of complexes. So in part 1, we have discussed about the color spectrum. First one is the color spectrum, and second one, how to determine the color of the transition metals based on the color spectrum. And third one is the factor that affect the difference of the delta or crystal field splitting energy. Okay, then for this part 2, we are going to discuss about the spectrochemical series and also the magnetism, right? So from here, this is actually a spectrochemical series, okay, the spectrochemical series. And as you can see from here until here, this is where we have the trend of the increasing value of the delta, right? The larger the number of the delta, the stronger the ligand itself, okay? And then what is the spectrochemical series? Okay, it actually has the ability to split the d orbital energy, and it can be used to predict the relative size of the delta for the same ion. Okay, and third one, it use wavelength, okay, to determine the complex absorbance. Okay, so this is where we have the absorption of light, okay, by the complex ion. Right, from this value of delta and also the types of ligands, okay, right, we there is two, okay. Sorry, based on the value of the delta, you can have two kinds of complexes. First one, right, here, for example, I show you the diagram, the CFSE diagram for the octahedral compound. Okay, for example here, alright, based on this spectrochemical series, we can have two types of complexes. First one is the low spin complexes, where you have the strong field ligands. Okay, right. For example, here we have CO, carbonyl, cyanide, and so on. Okay, so the difference between the T2G and EG here is bigger compared to the high spin complexes, where you have the presence of weak field ligands. So the difference between the T2G and also EG here, the energy difference between these two levels is much more smaller than the low spin complexes. Okay, alright, because of the types of ligand. So you need to be able to differentiate, okay, which one is the strong ligand, which one is weak field ligand. So this is a summary of the spectrochemical series, where I have given to you the same statement before this. We have two factors, types of ligands, and also the oxidation state of metal ion. And then this is where we have the types of ligands, from weak ligand to strong ligand, weak to strong. And then this is weaker field and strong field. We have a smaller delta and also larger delta here. And for the weak field ligand, they are actually absorb longer wavelength compared to the strong field ligand. They are actually absorb shorter wavelength based on the color spectrum. Okay, and right, so for this one, the coordination compounds are actually colored because they absorb light in the visible region. And other than that, we need to have empty d orbital. And then, so when these coordination compounds absorb the light, okay, so this energy absorbed is used to move the electrons from one energy level to another. And then in coordination compounds, okay, the energy levels are spaced such that the visible light is absorbed. For example, here I have the 3d6 coordination compounds here, okay, So what happened here? This coordination compound, usually we will dissolve this compound in solvent, and then we usually run this compound using UV spectrometer. UV spectrometer.
Yes.
Okay, right? So the UV spectrometer. So what happened here? Because we pass through the light, so the metal or the coordination compound absorb the light. It will start to excite the electron because we have lots of energy. Okay, so what happened here, the 3d6 at lower energy here in T2G, one of them will start to jump the electron. Okay, jump the electron, and it will give you an absorption band or absorption spectrum that you can analyze, and you can determine the which one is the lambda max and so on. Right. So don't worry too much. You will learn more about the UVVs during your spectroscopy code. Okay. So don't worry too much. Okay. Other than that, the bonding in complexes. Okay. So because of we have the absorption spectra from the UVVs of different complexes, it will indicate the crystal field splitting energy, and then based on the ligand's nature. Okay, so we have two types of ligand, strong ligand and also weak ligand. For example here, okay, for example here, I have nickel 2 plus complexes, so this is 3D8, okay, right, so nickel is actually 28. So this is nickel, and then the electron configuration for nickel is Ar4s2 3d8. Okay, and then we need to have the nickel 2 plus, so it will leave you with Ar 3d8. Okay, right. So in this case, we have three types of ligands. Okay, we have three types of ligand. First one is water, weak field ligand. We have ammonia. This is intermediate between weak and also strong. And last but not least, we have ethylene diamine. This is an example for strong ligands. Okay, so what happened here? From weak to ligand, you will be having a difference in terms of the delta. Okay, right. So in first example, nickel. Okay, this is hexa aqua nickel 2 plus, appears as green color. Okay, why? Because we have a small delta here, because of the electron itself. Okay, can jump to higher energy. Okay, can jump to higher energy because, okay, it is easy to jump to higher value because of the small delta here. And then second one, we have hexaamine nickel 2, okay, complex ion here, appears as blue color. Okay, it's also it is similar to the nickel with water, but in this one we have a larger value of the delta because of the types of the ligands. Okay, and then last one, we have ethylene diamine as ligand. So this is the tris ethylene diamine nickel 2 ion. Okay, or nickel 2 complex ion, appears as violet because this nickel has larger differences between the T2G and also EG. Okay, so these three, okay, you can differentiate the colors of these three because of the presence of their ligands. Okay, right. So other than that, the magnetic properties of the transition metal complexes, this splitting actually is splitting influence magnetic properties by affecting number of unpaired electron in metal ion of the d orbital. Okay, so when all lower energy orbitals are half filled, so the next electron we have two situations here. First one, it will enter half filled orbital, and also it will start to pair up by overcome the repulsive pairing energy, or what we call energy pairing. And then second one, enter an empty orbital by overcome the delta. So this is what happened in the previous example here. Right, the electrons actually try to overcome the delta and start to jump to the higher value, okay, or to the higher energy level, the Eg. Okay, and then the relative size of energy pairing. So energy pairing, they actually have tendency to pair up, okay, instead of overcome the delta. So the relative size of the energy pairing and also delta can determine the occupancy of the d orbital. Okay, so for the example here, we have iron 2 plus with d6 electron configuration. Okay, so it is actually an octahedral compound, okay, that can have either 4 unpaired electrons where it will form a high spin complex, or 0 unpaired electrons which will form a low spin complex. So let's look at the first example. First one, this is where we have the hexa aqua iron 2 ion. Okay, it has a high spin. It is actually a high spin complex with paramagnetic and attracted to a magnet. So what happened here? Okay, in order for you to draw the diagram of this compound, okay, right? So first thing, as usual, don't forget the energy. Okay, and then you need to have the T2G energy level and also the Eg, and because this is a 3D6, okay, with the presence of weak field ligand, this is weak field ligand, most of the time it will become high spin. So what happened here, you need to fill up the 6 electron, 1, 2, 3, 4, 5, and also 6 here. Okay, why? Because all the electrons has tendency to overcome the delta. Because of the delta here is small, you need to show whether it has small or large value of the delta. Okay, so this is the diagram for the iron 2 plus, okay, for in the presence of weak field ligand, and it will form a high spin complex. Second example here, I have a low spin complex and also a diamagnetic compound and not actually attracted to a magnet. For example, here we have this is -6, this is 4, so this is +2, right? So we have hexacyano ferrate 2. Why ferrate? Because this is -4. Okay, hexacyano ferrate 2, where if you want to draw the diagram, so first of all, don't forget to list the energy, and then this is the T2G, and also this is Eg, and this is also we have the 3D6. Okay, so first thing you need to fill up singly 1, 2, 3, 4, 5, 6, because this one it has a higher energy pairing compared to overcome the delta. Because of the delta here is large, it's not easy to jump to the from T2G to the Eg, right? So and then as usual, I leave you with exercise. We have first exercise and also second exercise. Please do this at home, and we will discuss this one during our meeting. And I think that's all for today. This properties of complexes. So if you enjoy this video, please don't forget to like, comment, and also subscribe my channel. So I'll see you guys in the next video. Bye.